So these blocks that we use to help with multiplication, the submatrices, we can also sort of use them to switch between the different point of view, especially when the blocks are going to be columns. Where this is useful is because the next things that we're going to see are going to be equivalent, right? We can write a linear system such as x plus 2y plus 3z equals 4, and x minus y plus z equals 2, y minus 3z equals 0 in the unknowns x, y, z. That's a linear system. It's non-homogeneous because the right-hand side isn't just a bunch of zeros, right? It's a system of three equations in the three unknowns. And that's exactly the same thing as writing the matrix equation a times x is equal to b in the unknown vector x. So now the unknowns aren't x, y, z, although we can write x as x, y, z, or x1, y1, z1. And a is the coefficient matrix, and b is the constant vector. And finally, the vector equation, where we're trying to solve for 1, 1, 0, 2 minus 1, 1, 3, 1 minus 3, 4, 2, 0 in the unknowns x, y, z. The first two, straightforward, we're trying to find the values of x, y, z that solve the system. In the third one, the way it looks is we're trying to figure out if 4, 2, 0, this thing here, is in the span of these three vectors. So this setup here is to find out if you can write a vector as a linear combination of what? Of the columns of A. This here is the first column of A. This here is the second column. So you have that the system has a solution if the constant term B is a linear combination of the columns of the matrix A. More than that, you know that there's only one solution if there's only one linear combination of the columns of A that gives us the constant vector. But if there are more than one ways to combine the columns, then you'd have infinitely many solutions. So you can think of solving a linear system, or you can think of trying to find linear combinations of columns. And you're really doing the same thing, even though it might not be obvious from get-go. In all of these cases, you would find the answer, the solution of the system, solution, or finding one linear combination, by row reducing the augmented matrix, by putting it in echelon form. So you start with the augmented matrix AB, which in this case would be 1, 2, 3, 1 minus 1, 1, 0, 1 minus 3, and we augment that with the constant column vector 4, 2, 0. We'll just row reduce this and read off the solution. If you think of it in terms of block multiplication, the columns of A, let's call them C1, C2, and C3, then A times X is really block multiplication of C1, C2, C3 with X, Y, Z. And this is true for any A, not just coefficient matrices. If A is equal to the collection of its columns in a matrix, then A times X, here should be a vector, A times X is linear combination of the columns of A. So A times X is a linear combination of the columns of A with the coefficients that are in the unknown vector X. AX equals B is consistent if and only if B is a linear combination of the columns of A, because then the vector equation has a solution. And AX equals 0 has a unique solution if and only if the columns of A are linearly independent, right? Because that third thing says, if you look at A times X equals 0, that would be X1 times the first column plus X2 times the second column, all the way to Xn times the nth column is equal to 0. So you're looking for solutions of the dependence equation, the dependence relation, And for homogeneous systems, we know that for sure x1, x2, x3, xn equals 0 is a solution. If the columns are linearly independent, there's only the trivial solution to this. And so the trivial solution, x1, x2, x3, all the way up to 0, is the unique solution in this case, if that's the case. It's like, okay, so it's possible then that the constant vector b is a linear combination of the columns. It's possible for the columns to be linearly independent. We're talking about the columns enough that it is worth introducing a new subspace. And it is going to be a subspace because it's the span of a bunch of columns. And we saw in chapter 2 that the span of any vectors is a subspace. Subspace of what? I say it's a subspace of Rm because A is a matrix with m rows and n columns. So every column of A actually has m components, right? There's n of them. That subspace, call A, we call it the column space of A. And it's an important space because we've seen that solving AX equals something does hinge on what the span of the columns of A looks like. So there's two important theorems which I will not demonstrate. You should try to see if you can show that these theorems are true. Assume you have an m by n matrix. The following are equivalent, meaning that if you have one of them, you automatically have any of the other ones. If you don't have one of them, then you automatically have none of the other ones. The column space of A is the full space Rm, the entirety of Rm. The columns of A span Rm. Ax equals b is consistent no matter what the constant vector b is. And the RREF of A, just A alone, contains no zero row. So there's a leading one in every single row of A. Now, all of this is clear from the definition, but you should verify that you can indeed prove that this is the case. Here's another theorem that also talks about the columns of A. Again, have a matrix A, which is an m by n matrix. Following are equivalent. If any one of them is true, they're all true for a specific matrix. If one of them isn't true for a matrix A, then none of them are true for that matrix A. The columns of A are linearly independent. Ax equals 0 has a unique solution. There's a leading one in every column of a reduced echelon form of A, and the rank of A is equal to the number of columns of A. So now we'll take for granted that we know this to be true. We can combine all of these things together in a theorem, a nice theorem about square matrices. Here we're assuming that A is an n by n matrix. And again, the following are equivalent. The columns of A form a basis for Rn. The columns of A are linearly independent. The columns of A span Rn. We know that if they span Rn and they're linearly independent, then they certainly form a basis. But for square matrices, you just need to show one of them to know that they form a basis. The rank of A is n. So there's a leading one in every column of A. There's a leading one in every row of A when you reduce A. The column space of A is the whole of Rn. The columns of A span Rn, and no reduced echelon form of A has a zero row. So all of this is just a repackaging of the previous results where m is equal to n. That's a special case, right? If we have a system with the same number of equations as the number of unknowns. whereas the previous results were true for any random matrix A of any size.